Okay, hi. So the time is 8:30. I understand that there's a lot of requests for the lectures to be done on MS Teams. Tell you what, I will take a look at that to see how we can get that up and coming. If it happens, we'll try to do it either this Thursday or starting from next week. But okay, but other than that, thank you guys for coming here. So I'm not sure why there's so much items on issues on this muting thing, but I hope everybody can cooperate to just have a good Scott learning session. So okay, so hopefully the slides are already online. So it's on distance, so you can go there to download it. Yeah, and yeah, thanks, Winston, for the reminder. Don't forget to mark on your attendance. It is there. So one of the main reasons I'm using Zoom is because or rather the easy usage of the backup rooms. So that's why we are using that. But I understand your issues on the muting of the mics. Okay, but anyway, let's move on from there. We are already 2 minutes into time. So the key takeaways for today will be, yeah, Miss In has a question. Yes, the lectures are all recorded. In fact, I already started recording already, and I'll be uploading them probably to YouTube, and you guys can view the recorded lectures from there. Yeah, it's quite strange, right? So I try to mute them as they come along. I'm not sure why. Okay. So anyway, the topics covered in the class will be the key takeaways for this will be to know the topics that we covered during the entire 211. The reasons for using a database. Maybe we'll go through some preliminary of what databases are, and then some architecture of database as well. So yeah, let's go ahead. So the motivation. So there's a lot of data that's really coming out every day. So for example, the NYSE has 4 to 5 terabytes of data per day. Facebook hosting goes at 7 petabytes per month. Internet Archive stores for 18.5 petabytes of data. And really, we can sort of foresee that the growth of data is probably not going to stop. And so there's always a need to be able to, in a way, manage this data well. And number of jobs available. So this was a very simple scraper that we did. I think I did this 1 week or 2 weeks back. So I wrote a simple scraper to find out the number of jobs in Indeed, JobsDB, and JobStreet. I compared it with the number of software engineers. Of course, the number of software engineers will be very high, so about 3,000 plus. But you will notice that the number of jobs that are available for machine learning, data science, not too small as well. Interestingly, the number of jobs for data engineers are actually very small. Yeah, but you can notice that although in relative terms, like software engineer has more job posting than all the rest, but it's interesting to say that, and definitely very correct to say that definitely a lot more people train in software engineering more so than machine learning. So there probably is a little bit of in a way, I will put it, you can see a little bit of shortage in terms of people that's skilled enough to fill the roles for that of machine learning, data science. Whereas for software engineering, there are a lot more people that are trained in it, but yet the number of jobs available, not that much more than that of ML or data science. But the interesting thing is that if you go deeper in one level, into the job titles that are available, the job titles that are there, although there are very few postings in data engineers, but you notice that for data science, for machine learning, the top words that emerge out are in fact data engineer. So it counts for the fact that I believe is that the requirements of the job really is that they must be proficient in the engineering of data. But the thing is that if you call a role a data engineer, it probably is not as glamorous as calling yourself a machine learning software engineer or machine learning scientist or data scientist or AI engineer. So I would think that the probable case is that the job title of data engineer isn't as appealing, and so they will get less recruits, or at least less people applying for it. And so they will use terms like AI or data science or machine learning in order to prop up the number of applicants. But if you look in depth into what the title entails, right, you notice that it is still data engineering that is on the top, and this is only the job title. If you go one level deeper into that of what the description of the job title is. So again, data engineer, data, it comes out as the very top. And here it becomes very, very clear. There's a very strong distinction between the first four terms, data engineer, AI, data science, machine learning, versus that of software engineering. So you can tell immediately the distinction. These four roles that are available, they are very, very data centered. Whereas when we look at software engineering, they talk about development, software development, life cycle, which is very, very crucial part of the software engineering process. But the data comes quite not as crucial or critical as what the other roles are required. So it is then very, very clear that there's a very clear demarcation between these four roles versus that of software engineering. And again, this highlights the fact whereby data is only going to increase in terms of importance, and hence that's why we are here today. Topics that we're covering. So there are several ways whereby data can be stored. So we can store in file systems, CSV files, in graphical form. What we will be focusing on for this CS211 will be that of a relational database. So in relational database, we typically store, we call it relational database, but it is because we typically store them in terms of tables, as what we will see over here. So yeah, and tables, they will relate to one another by certain fields. So because the fields may correspond to one another, and hence the term of relational databases. For relational databases, there are a few common things that people normally do. One will be data modeling. So you have, this is what they call an entity relational diagram. So ER diagram. So you have, you store the entities, or rather you describe the entities in terms of an ER diagram. Usually from these entities, you convert them to a database design, and then from here on, then it gets transferred to your tables, which goes into your SQL. This definitely looks a bit like your so-called your class diagram. These actually these definitely look similar to your class diagrams that you're probably very familiar with. Yeah, so you can do a simple correlation between relational databases design versus what you are very familiar with. This will be one part of the course. The second part of the course will pertain towards NoSQL. NoSQL means not only SQL. So SQL does a lot of relational databases. For NoSQL, we call them documents. So it will be stored in terms of documents, and typically they store in terms of JSON entities. So this will be another topic that we will be covering during this course. Maybe to share a little bit of background on this. This is the second time I'm teaching the course. I'm still in the midst of rewriting the course so far. Early this year was the first time I taught the course. It was a little bit, there were some parts that I thought was a little bit theoretical. In this installment, at least we'll be trying to make things a little bit more practical. I'll try to incorporate certain practical aspects into the entire, both the lectures as well as or rather primarily the lectures, and also hopefully I can do something a bit more fun also in the assignment projects as well. This course, fortunately, will be totally online. So you have to think further on down the road how we want to conduct the various quizzes. So yeah, so we'll manage these things as they come. Sorry. So in terms of relational database, we'll be talking about data modeling, database design, ER model, as I shared earlier, entity relational model, functional dependencies. So we have tables. Some of these tables depend on one another and how they depend will be one thing that we will be talking about. Some of these are also, let's say, they are characters. So how should these fields be structured? So these are just some minor things that we'll be going through. We'll be looking at SQL, which is the language that will be used to interface with the so-called relational database. So typically, you have the data that is stored here as a table. SQL, which is select star from table where a certain condition occurs. So this is that of SQL query. And typically, we will be asking for items from the table based on the SQL query, and this is somewhat the syntax. So in terms of query, usually we have these four terms, CRUD, which we'll go through later on. So create, read, update, and delete. So these are the four key things that we usually look for, or rather we need to be able to do whenever you are carrying out database. So every time you set up a database, you have to set up these four functions. These are your fundamental basic four functions that are there. We'll be doing these will fall under basic SQL. We'll be also looking at advanced SQL as well. Advanced SQL will be about aggregation of views. Aggregation will be, for example, counts the number of people where maybe GPA greater than a certain number. So these are all aggregational functions that are there. We'll be talking a little bit on integrity where I create trigger. So what this means is that if a certain condition doesn't fit into whatever rule that you have set up the data table to be, it will sort of trigger a sort of a response for the database administrator to understand that that something needs to be done there. These will be all under relational database. It will carry probably about 70% of the cost, 60 to 70% of the cost will be all under relational. Then we'll be doing a switch over to MongoDB. So MongoDB will be talking about NoSQL collection database syntax. How do we do query? So basically, it's really to get you guys used to the concept of NoSQL. We'll be covering concepts of JSON, what JSON documents are. Then after that, how should we be designing MongoDB databases? They're actually the entire mindset is actually very different. The way we manage data. So you realize that in fact, when I first got hold of it, I was I felt very odd. Why? Because in relational databases, the key thing you want to focus on is have little redundancy. So that is what relational database go for. But in NoSQL, it is the direct opposite. You actually want redundancy, which is at the first onslaught, it was very strange. Like why would you want redundancy there? But you realize that it's actually built in for a reason. Why? Because joins are very expensive. But I'm going ahead of myself. So yeah, let's go ahead. Let's go for it. Yeah. So you'll be learning things on that front. You'll be looking at generic database content. For that, you have web servers, APIs. If you have time, we'll be touching on Apache Spark. So in the last run that we did early this year, one of the comments that was given was that they don't know why they're learning this at all. So they don't understand how does this fit into the context. So like how is database actually being used initially at all. So which I think is really good to run a few lessons on this part. This will constitute probably the last 10%. So this will be what web servers are, how database can be hosted on the web server. Yeah. And we talk about how APIs as well, or rather maybe you can APIs hosted on web server. Yeah, yeah. So this will be the next 10%. If we have time, we will go on to Apache Spark. So Apache Spark will be extra. So it will be a bit extra. Why? Because this will deal with distributed data, distributed. So all these assume that we are under. I've run out of space. All these assume that we are under a monolithic, so-called kind of framework. So monolithic is that if your database is here, so this is at the start. Let's say this is 2004. So your database is so you work, and then your database grows, your user base grows, and you run out of database here, database space in your server. So in the monolithic framework, you then buy a bigger server. So of course, then you start from here, and then you start to build up again. And if you run out of space again, you then buy another bigger server that will be bigger. So of course, the issue with this is that the cost. Let's say this is 1 unit of space, and this is 3 units of space, and this is 10 units of space. So the biggest issue is that the cost of this is greater than 10 times the cost of A, B. The cost of C is going to be 10. The cost of C is definitely going to be much higher than the cost of A, and the performance of C will definitely be less than 10 times of the performance of A as well. You probably will get you get the space that you require, but you probably won't get the performance, and you come at a much higher cost, which is why the concept of microservices is so popular in this time and age. Yeah, and with that we will be talking. So when we talk microservices, we talk about distributed computing. So when distributed computing, your database may not sit in one particular location, or rather your data may not sit in one particular location. It may be spread out across multiple areas, and with that you then need another so-called processing engine in order to interact with all your distributed data. And this processing engine that we have called Apache Spark. So this is what we will aim to be carrying out for this course, this particular run. Any questions so far? Okay. Okay, that's good. So go back on to the first topic. Why do we want to use a database? So for example, if you want to store info of university, you have instructors. So you probably have various items, classes. We call it entities or classes. So you have maybe like instructor entity, student entity, department entity, course offering entity. So you have this information. How are we supposed to store them? So one way of storing them is we can store them in files. So store them in documents. So document and instructor, and then a student. So you can read this in a single list. So like that. So instructor A, B, C, name, maybe uni, name. Yeah. So you get the idea. So in student you have ID, you have name. Maybe you want maybe GPA, yeah, GPA. Yeah, so this can be, in a way, if you were to not have a database, typically this is how you would do it. In fact, and I may be wrong on this. I understand that from your colleagues that took the course early this year, this is also typically how you would store your database in a game. From what I hear, and also from some research that I did, people do that also in a gaming context, right? Because the amount of data that you may need to store in the game itself may not be a lot, and you want it to be as fast as possible. So you want it to be able to load everything in the memory and be able to access everything in memory itself. So that was what I understand. I may be wrong, but that was what I understand from some reading that I did. So what is the issue with this? The first person on my list is actually a gentleman called Ryan, Mr. Ryan. What is the issue with storing data in this manner? Are you there, Mr. Ryan? Do you have your microphone on, or is it inconvenient to unmute it?
Hello, can you hear me?
Yeah, yes, I can. Yes, we can. So I'd like to ask you a question. So what is the issue if we were to store data in this manner in singular files? What do you think is the issue?
If you're talking about the files, probably got a lot. The OS need to like a lot of overhead, I guess.
Yep. Very good. Thank you so much. So Mr. Ryan mentioned that that the OS may cause a lot of overhead because you are going to be interacting directly with the file systems, and you're going to be reading a lot of files here and there. How about can I hear also from Mr. Wong? Are you there? Mr. Wong Kim K?
Yes, hello.
Hi, Mr. Wong. Yeah, so
Yes.
do you foresee any issues if I want to update something with this particular type of file system?
Is it unable to store all the information you want?
Okay. May I ask why were you what is there a reason why for that?
I'm not too sure. So
No worries. So no worries. Thank you, Mr. Wang, for sharing.
okay.
So yeah. So it's good to try. Why? Because and it's fine because to be frank, all of us are learning from one another. So maybe a bit of background. I'm actually from SIT. I'm not from DigiPen. So so yeah. So I mean, my background is not exactly in terms, not exactly database technology as well. So there's also a lot for me to learn and pick up along the way, and we're all here to learn from one another. So, but in this case, right, if we were to store data in terms of file system, right, the issue that we will face, right, is that it may be very hard for us to update certain items. So for example, right, if I have a file, and this is student 1, and this is GPA, and this is let's say this is AAA, and this is 4.3. And one day after the trimester is over, I need to update his GPA. So it means that I need to load the file. I need to search through every single student here, and need to look for this guy AAA, and I need to update this number. If we do it in a sort, at least it may still be just log n. But if it's unsorted, then it's going to be n for every student. So if I n students, then be n squared. So this is definitely not a good way of doing it. And whatever updates that I need to do, whatever things that I need to carry out, it will be a lot more complex. And the way that I store it, be it a sorted system or is it an unsorted system, right? Regardless of that, it is to the owners of the developer to create that. Meaning that if I want to store this as a sorted data structure, then it is on the owners of the developer to put a sorted data structure in order to store it in that manner. So then it becomes very heavy for the developer itself. Whereas if we use a database, in a database, actually everything is stored as a B plus tree, or typically it's a B plus tree. And because of that, this kind of data structure is already inherent, built in into the SQL itself. So we don't, as a developer, I'm able to extract out this entire layer, and I can use the SQL queries to insert, delete, update whatever information that I require. So I don't need to. I don't really need to. Yeah, it's much easier for me in that sense. So this is one of the biggest issues with this. And of course, if I have multiple files, it means that I have to search multiple files in order to insert one record in to make sure that there's no overlap between my, or rather yeah, I'm not inserting the same record twice now. So you can imagine that it's definitely something extremely challenging to do. And yeah, how do we interact with the program is really hard. For example, I was saying read, writing, updating, operations are actually very, very hard. So imagine if I want to return the average score, average GPA, means I have to scroll through every student to get that. It's really a painful operation. Yeah, creating of class rosters, generating transcripts. Yeah, they're all extremely difficult to do if we use it as a file system kind of context. So then what's the purpose of the database? Sorry, it is primarily to store the data, provide organizational structure for the data, provide mechanism for querying, creating, modifying, deleting data, and functionalities, keeping consistency, easy access to data, keeping integrity, supporting concurrent accessing, security, and these functions. Okay, so you can just read these yourself. I'm sure. Yeah, it's just quite some background information for you. Potential issue, some additional so-called elaboration. So if I want to add in a new student, I have to input the student info, ready to file. But before that, I have to check for duplicate first. So I was saying earlier, if I have a John Yo here, I have to go through all my records. Check. No duplicate. Then I insert in this new record in. Okay. So this is one of the big issues with just for this. This is the first example. In the second example, if I have my, if let's say I have a CS211 and my name of it is database, DB, and supposedly if I want to change my my name of my course from DB, I want to change it to the full name database. It will actually trigger off, or rather, if I store it as a file concept, my individual files will not be aware that I actually changed this. Whereas if it was a database, because this may be a foreign key, maybe I don't say this first, but this may be a relation, and it may cause a trigger to occur, which will also trigger the change of this cell, this record. Okay. Okay. So if I want to do retrieval, so so if I want to retrieve, display the students in the enrolled class, I can display all the students from the enrolled class. But let's say if the student is missing, meaning that the student is in another file. There's another student file here. I have to search for the student file. So I want to just to display the enrollment of one of the modules. I have to search the student module to find the corresponding entry in the in the student file. Okay. Any questions so far? All good? Okay, so this is the first solution. The second solution, I can add another field student name into the course enrollment file. So meaning that I have in the original, this is the original. I can add a student name here. So it allows me to have a student name as another field. Of course, the issue with this is that there is then no redundancy. In this case, right, the redundancy is little, but it is somewhat can consider to be a little bit acceptable. Why? Because right, you probably don't change the names very often. So although you have some redundancy here, but it's not every day that the student changes the name. So even though there's some redundancy here, it is still, I wouldn't say acceptable, but it can be managed. It can be managed. Yeah. Later on during the course, when we do database design, you'll be learning about how to assess how good or how bad a certain database design is. But just a note for now, this increases the redundancy, but it does keep the integrity of the data. So if you want to delete, the student, I need to really delete off the student from the student file. And I also need to know that from my course enrollment file, this student is enrolled into it as well. So I need to delete here, and then delete here. So all these need to be understood by the developer that these are items that I need to be done. Okay, so far. Okay, good. So this is an example of a flat database file where I combine every single thing into one large file. So this is the extreme case whereby instead of having several files, I will keep everything into one single file, and I will have all my fields being held in that file. Okay, let's look at this. Is there a Jia Wei here?
Yes, I'm here.
Mr. Jia Wei, may I ask what is the issue with these two lines?
They have a lot of similarity.
Yes, correct. Very good. Thank you, Mr. Jia Wei. Very correct. So there's a lot of redundancy. So they call this redundancy. So there's redundancy here, and also there's redundancy there. They're actually storing the exact same thing, and so this is not ideal in terms of database design. Yeah, exactly. That's the first point, and the second point that we also may want to point out is that there's a lot of repetition of information. So, for example, physics in building Watson, it is somewhat still okay. Why? Because right, you probably this will be in the building Watson for many years, so we doesn't change often. So it's still relatively fine. But the thing is that the budget probably changes every few months. So every time the budget changes, you have to search through the entire file to update the new budget into the so-called the corresponding fields. Okay, the second point. The third point, okay, third point is I'm able to create a building department name with no faculty. So every single building and department is tied in with a faculty. So if I want to create a building with no faculty, it'll be something like this. Now, then let's see, I have one new department called law. I have no law here. Law, maybe law building. And so let's say if I want to create a new department called law, there's actually no way for me to create this. I mean, there's a way, but the rest of the items need to be now. So may not be the most ideal case because why will you need to have that to be the case? It doesn't really hold water. So yeah, this is not a good solution to that. Actually, another more important case is that let's say if let's say if I have two guys here from physics department, and let's say if Mr. Goh retires, and then let's say, sorry, physics is not physics. Let's say Mr. Goh retires, and Mr. Einstein, let's say he gets headhunted to another university, and so my fields of physics, Watson, and this number will be gone forever. It actually will be gone from my database. I need to explicitly create a now physics Watson 7000. So there's a lot of things that the developer actually conditions that the developer has to take note. So even in the deletion of a certain so-called faculty member, he needs to ensure that there is still at least one faculty member that's there. Else, they will have to create so-called placeholder fields such as these. So yeah, so that is the idea. That's the issue. One of the issues behind these flat files that I'm trying to explain. So yeah, that's what I was trying to say. So of course, the way to do it, or rather one of the ways to do it, is that we split the data into two files. In our context, right, it is actually two tables. So in relational context, the tables are actually linked by this. So every time I want to know what is the budget for let's say for maybe for Mozart, then I can search select so-called budget from I just I don't write the rest, but from this table and this table where this table dot name equals to Mozart, and this table dot department name equals to this table dot department name. Yeah, so there's a way, so splitting out the tables like that allows me to construct the SQL query in order to sieve out this information in a very quick and fast manner. Okay, so far? Okay, very good. No, hope you guys are there. So I hope I'm not talking to myself. Anyway, so okay, some preliminary understanding of relational databases. So we talked about CLUD. So CLUD talks about create, read, update, delete. Something that so I talked about that earlier. The other thing that we want to talk about is this atomicity, consistency, isolation, durability. This means that either the transaction succeeds or it does not succeed. So, for example, right, in terms of is there a Mr. Andy? Mr. Andy Chan? Yeah. Can I ask in terms of let's say a bank transaction, if I want to transfer money from person A to person B, how do we understand atomicity in that context? The payment get through, either that or yeah. Okay, no worries. Thank you, Mr. Andy. So in terms of that, right, there is only two conditions that can occur, meaning that either the payment gets through or either the payment does not get through. So either the person receives the money that that's sent to him, or he does not receive the money that's sent to him. There's no in between the two. So there's no like, there's no nothing like I'm going to transfer $1 from A to B, and there's nothing like A and only 50 cents get transferred. Yeah, so nothing like that will occur. Or we will also not hear something like what's another example, like I think this will be one of the main things that you may find out maybe later. Yeah, so it's either yes, transfer okay, or no, transfer not okay. So it's either one of the two. It can't be anything else. So this is similar to that of databases. Either your transaction is successful or it does not successful. Yeah, Miss In had a good point. Yeah, it's either 0 or 1. So either it succeeds or it does not succeed. Yeah, so it's either one or the other. For consistency, all data will be consistent to a set of well-defined rules. So there'll be certain rules that we would in a way have to define. So for example, if this is student ID, so it may be an integer. So if this is something, it may be a var char 20. So there will be certain rules that we will put in place of the various fields that are there, and the data has got to be consistent with these various parameters of the rules that we put in. Okay. Isolation, all transactions will occur independently of other transactions, and a transaction cannot read data from another transaction there. So meaning that if I were to transfer A to B, so-called A to B, and then I want to transfer A to C, then this is $3, this is $1. In a way, this transaction will be independent of this transaction, and I'm going to make assumption that I have enough money in my bank. So this transaction is going to be independent of this transaction. So if I have enough money in my bank, there won't be a situation whereby because this pass, so this fail, or because this failed, so there won't be a situation whereby each of these is dependent on one another. So they must be independent from one another. Last would be durability. Once a transaction is completed, it is going to be stored permanently. So so that is one of the so it won't be lost suddenly lah. Hopefully it won't be lost suddenly. Yeah, but that is the last property of relational databases. Okay, so a relational table, this is at the heart of every relational database, which is called a table. So this is a typical relational table. We have the name, we have the GPA, we have the size of the class, I think, of the school. Yeah. Okay. So it's quite clearly what is there. So the table is the relational. The entire thing is table. It's a table, and there's a relational schema. In this schema is the concept of what these various fields have. So this is the table format, which is SID, SName, GPA, and size HS. And all of these will have a very so-called a certain attribute that's being given to them. So for example, this one may be integer, this may be string, this may be float, and this may be maybe integer as well. Yeah. So there will be a so-called a table name as well as a format that the data has got to follow. And there will be certain lines that are there. Each line is known as it can be called a line, a tuple, or a record. So that will be count for each individual line. Okay. Each column each column. So this S name is a column. There'll be, they call this column name, and then there'll be certain values that in the column name. Okay. So this is the entire breakdown of what a relational table looks like. At the heart, this is the base construct of what a relational table is. And it is usually planned in a manner whereby certain tables are linked to one another. So you don't need to go through this for the time being, but usually you end up with something that looks quite similar to this. So the schema describes the structure. So in the structure you have, so there's over here, there's character, there's variable character, GPA, which is a real number, and an integer, which is the size. Okay. Oh, good. Okay, so in this case, in the relational table model, I can have a few so-called a few different schemas. So these are two tables. So in this schema, I have a student. So student, I have student ID, name, GPA, size of the college, and over here, this will be the name of the college, the statistics, and also the enrollment number. So this will be the various schemas of these two different tables. So of course, so what we are talking about is that in this entire relational model, we have two different tables, or you can call them schemas, and these are the two schemas that are there. So there are various types of data models. So we have a relational, which is what we're going to learn today, rather this trimester. Hierarchical, you probably won't do this, or even network, we also won't be doing the other two. Yeah. So just to put this, there are more than one type of data models that are available. Yeah. So let's illustrate this with a simple book management system. The time now is 9:18. I think it is actually good for us to take a very quick 10 minutes break before I go into this. So I tell you what, let's take a very quick 10 minutes break. We'll reconvene back at about 9:28. In the meantime, I'll stay around for a bit longer if there are any further questions. Thank you. Okay, the time now is 9:28, and we'll continue. A few questions come up. Maybe the one that I can address immediately is DBAP. DBAP stands for database application. Yeah. So that's the okay. So there's a question on earlier on asking on elaboration of slide 28. So I talked a little bit there. there's a follow-up which asks what if the change requires to update multiple tables. So there's a command in SQL called on change cascade. So when the particular change they need to do affects this table and maybe some of the other tables that are there, right? Then with the cascade command, it will actually sort of cascade these changes down to, or propagate these changes down to the other table. So as a so-called as a developer, we don't need to explicitly change all the tables one by one, but we may want to be sure of when are the cases whereby we may need to do this cascade operation, and then we can simply carry it out. So yeah, so I hope that answers your question. Okay, so that's good. I will continue. So was I here? Was an example? Hold on, I thought that was this is it's here. Yeah, so I was here. Sorry. Yeah. Now illustrate this with a book management example. So in this book management example, we have a database that is here. So this is the database. This database management system. Database management system MS SQL. So this will be somewhat the interfacing with the actual database. So these are all the so-called the management systems that are there. Administrator will be the ones to manage this database application. So this is typically your front end, how you interface with so-called your DBMSs. Yeah. So typically this is how the management system may look like. So from the user point of view, you only look at these two items. So look at the data definition language, which is how your table is being defined, and also the data manipulation language. How do we manipulate this data, which is basically your CRUD operations. And primarily, we will be doing more of these two points in our course for 211. We probably won't be talking that much about it. Yeah. So in the data definition language, we have things such as create, drop, alter, truncate. So basically, it's really your CRUD. Actually, both are quite they both have similar CRUD elements, but these actually deal a little bit more in terms of the actual schema that is there, and also the database structure. So schema of the tables, and also the database structure. Whereas for this, it is really more of actually this here. C is here. Already. So you have reading, you have updating, you have deleting. They usually fall under the data manipulation language, and definition language should be more in over here. Okay. But in our context, right, this is basically can be summarized more in terms of SQL. So SQL as a language per se is able to do both of these items. So let's look at this in how we would be working on the data. If you look at SQL, right, this is a typical SQL statement. Select. We'll go through this in more detail. Yeah, but select column name from table name, and this is the condition. So this is how typically we would write an SQL statement. So if I were to have a so-called MS DBMS site, maybe for example, let's say we are looking at PHP MyAdmin. So I'll be able to have a and execute, and it will then return. This is how SQL is being done, is being used. If you are using just the SQL alone, without you're looking at just the SQL language by itself. Of course, we also I also have two other examples here, which is the embedded SQL. So this happens if we use it. Let's say if we are writing a piece of code, let's say it can be this I can't remember, this looks like Java. I may be wrong, but this looks like Java. So let's say I'm writing a piece of code, and I think that yes, correct, this Java. Let's say I'm writing a piece of code, and I want to, in a piece of code, query a certain database. So this is how I embed my SQL statement within my code itself. So of course I have to first deploy the JDBC connection. So this would actually is like a driver to connect with my database, to be able to talk with my database, and then the various things will be the SQL, which then will be able to help me to retrieve whatever queries are there. So you can call this embedded SQL. And if we were to look at this from a high-level language perspective, right, then it will be like for each tuple, if we find that this condition occurs, we can on this. But yeah, so I put this there as an example of how we look at these queries, right, from a high-level language point of view. Okay. 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 So next, probably we will be more of up to here. Okay. We'll be doing things up to here. Yeah. So we will be learning about interactive SQL. This we may be doing a little bit of this if we if we are able to do web servers. We will then be able to do carry out this portion. Data modeling we'll definitely be doing because we'll be talking about ERs and also normalization. So we'll be looking at normalization is how good or bad the DB is. DB in a way. So we probably won't be talking about these two parts for this lecture. For 211. Architecture, there are two types. So there are the 3-tier types and the 2-tier types. So maybe a little bit more. I combine everything together. So I was supposed to display this out step by step. So the first tier is so this is the tier 1, tier 2, and tier 3, where you have the application server and the web server. So this is 2 tiers. 1, 2, 1 and 2. Okay, so this is the difference between the first tier and the second tier. How we want to talk about this is that we'll be focusing more on the 3-tier types in this module. So we have in a way 3 different schemas. So we have firstly the internal schema, and then we have the conceptual schema, and then we have the external schema. Okay. So it's a little bit abstract. It's a little bit abstract. So what it actually means is that there's a way for you to understand how to how do I say? And there's a way for me to grab data, and then organize it in a manner to let the end user see. So for example, right, I can say select I can get everybody where from A where GPA greater than 0.3. So I get a list of names here, lah. But I may not want to display out all the fields here. I may only want to display out name and maybe year. So then there is an external schema that I'm actually doing as a programmer, which allows me to display this data, or rather only the required data out to the end users. And typically there's some kind of a mapping that is there. So you see there are two mappings here. So one is the mapping over here, where I'm, in a way, the developer maps what we have in our schema on the database to what is required to be seen by the user, and also the internal mapping here. This one usually we don't touch because it's actually managed by the database. Actually, this entire part is managed by the database. No, not by the database. So we only manage this as a developer. So the importance of this is that we want to be able to change whatever we want to see here without touching conceptual schema. So that's the important thing. We want to be able to so for example, if today the client wants to see ABCDE, then we'll be able to change that without touching our internal schema. The other thing is that this, although usually we don't touch, but it is important in the sense whereby earlier I was saying if I have distributed databases, so I may have one that is MySQL, and I may have another one that is a Hive, and may have another one that's a HDFS file system, Hadoop file system. So I may have various different types of databases, and I will have to they have their own internal schemas, and I will have a conceptual way to be able to represent them. So which is where I mentioned earlier the idea of Apache Spark. Then becomes very powerful, because Apache Spark is able to have a global view that allows me to connect with all the various different types of databases without having the developer do any additional work. Okay, so that's it for this part. So still relatively conceptual. I'll go into a bit more detail in the next set of slides. Question that was being asked. One of the questions was that they wanted to ask whether it's a private question, but I can share out to release the assignment in advance to do. So yeah, so I can certainly look into releasing the assignment earlier. No problem. Yeah, I can do that. Yeah, and then the other thing is which open source SQL software you'll be using. You'll be using MySQL, which what they call it right now is MariaSQL. So what we would be this is a little bit early, but you can download and install these versions. So if you're on Windows, you can download SMPP. If you're on Linux, you can download LMPP. So another question was asking, what's the point of having different types of databases? So usually we don't have the luxury, in a way, like sometimes we don't have the luxury of being able to store everything in one singular database, especially when your data becomes very, very big. And it's also very, very common whereby you have data from diverse sources. So for example, right, I have data coming in from sales data from this certain kind of file system, or rather certain type of a database. I have maybe let's say my database on sales data definitely is high volume and very, very fast. So it will probably fall under particular type of database structure or type. And I may have also another kind of database which is like what is the type of data that's been stored in. So those data is still relatively fast, but definitely the rate of change of it is a lot less than sales data. And those we may decide that we want to store them in maybe another type of database. Maybe the first type I may want to choose to store in the Postgres database. The second type I may choose to store in maybe let's see, just for argument, MySQL. Maybe another type of database which is the comments, people's comments, reviews. I may choose to store in the HDFS database as well. HDFS. So I may end up with having many different types of database, but I may want to have an aggregated view of my entire so-called sales inventory or sales. May want to generate a sales report, and so in order to do that, I need to be able to access multiple databases at the same time. So that's the main point. That's the main reason. Okay, I'm going to stop this slide. So I'm done with this. Happy to answer any questions. So I think it's always good to I mean, that's what I'm here for, yeah, basically. Let's try to go into lecture number 2. So this lecture will be on relational model overview. And the 3 key takeaways. One, to understand the conceptual foundation of the relational model, some characteristics of our relation. Keys, integrity constraints. Some of these items I have talked a little bit about them earlier this evening. So if I have, I may gloss over them if I've covered them already. Conceptual foundation of the relational model. It was proposed in 1970 based on a few things: the table, what we have been talking about, set theory to define data manipulation, first order predicate logic to define integrity constraints. This we will cover them a little bit later on if we have time. Set theory for data manipulation. We use, the main thing is relational algebra. So the SQL queries that you saw me write earlier, right? In fact, all the SQL queries, they in a way get converted to a so-called relational algebra, and then they get optimized, and then they get SQL. So which is why the relational algebra is a key part of whatever that we are actually studying today. So for example, set A union with set B, set A intersect with B. So there's also a select. There's a select, which is the sigma. There's also the projection. So select memory S name equals to Amy. Project out the GPA. So this is actually the I need a table name here. Table name. So this is actually the relational algebra conversion of select as GPA from student where as name equals to name. So this is the SQL version. This gets converted to the relational algebra version here. So and why do we convert it? It is primarily for optimization, which we will talk about more in later on in the course. The other thing is integrity constraints. So there'll be some constraints that you can put in. For this, to use first order predicate logic. I'll see if we have time to go through this in the course or not. So let's see how things go. Some things, we have entity. So we talked about earlier things that need to be represented in the database. So student, instructor, employee, project. Typically, but not every time, these have their own individual tables. But it's not every time. not every time. It's not a rule, but it is not surprising to see many of these become actual actual tables by itself. Yeah, typically it's the name of the table. Yeah, typically, but not every time. Yeah, typically. Yeah, so entity relates to one team, topic of business concept. So in entity, students, Amy Chu, where's Amy Chu? Amy Chu is not here. I mean, maybe it's this person, Amy Chu, is one of the instance of the student. Yeah. So if you put it into the class context, like entity is like a class, Amy is this this entire role is an instance of the student. So yeah, so role is instance of entity. Column, if we convert this to a so-called a class kind of understanding, a role is attribute of the entity. So the GPA is attribute. This is the instance. The next one is cell, is single value, which is the value of one of the attributes of an instance. And all the values in the column, they all have the same data type as what classes usually are. Every column will have the individual unique name. I think this is also typical of any class. The classes in your, they must all have unique names, and no two roles can be totally identical. They must always be different in one way or another. So the schema is actually the structure. So as I shared earlier, this is the schema of the table student. What's the point of having? Why can I post on lecture? Yeah, the slides are actually in Moodle already. So yeah, so you can download them. I think I posted them this afternoon or just before the lecture. I can't remember, or maybe I can't remember, but it's actually there already. It's actually there. And yeah, so this is a summary of what I mentioned earlier. So if we look at the C equivalent, right, entity can be called like a struct. Relational schema can be the definition of the struct. Instance is like instance of the struct. Attribute, one of the attributes of the struct. And cell is a single content of the struct attribute. So okay. So in this relational schema, I have A1, A2, and up to AN. These are my so-called table names, table attribute names. So it's going to be like this. So this is A1, A2, up to AN. And sorry, and up to AN. And every single attribute has a data domain. So this is what, for example, in this example, right, is what possible values can this particular so-called column hold. So in this case, it can be high, medium, or low. In this case, 1, 2, or 3. A3 is red or blue. So basically, this is what the relational schema and the data domains are supposed to provide. Okay, some characteristics. So okay, so based on the definition of the schema, so we can assume that, let's say we have this particular schema. The product of D1, D2, D3 is going to be equals to a certain value. So maybe let's see if we can ask anybody or not. Is Mr. Chong Jing Kiet around?
Yeah.
Never mind, it's okay. So I think the echo is quite bad. Never mind, I'll do this. It's okay. Thank you so much. Or if you want, you can type down if you want to also explain a bit. So I have now three A1, A2, and A3. And now I have three possible values. I have three possible values, and I have two possible values. So right now I have three possible values here, three possible values here, and two possible values here. So the total possible number of tuples would then be equals to 3 times 3 times 2, which is equals to 18. So meaning that if A1 is able to take high, low, medium, and A2 is able to take 1, 2, 3, and this is red, blue, then the total size of this table, the maximum, is only going to be 18. And why? Because these are the total number of so-called permutations that the table is able to make. Why? Because there can be no duplicates. So every single row must be unique. So because every single row must be unique, there are only this certain number of values that these numbers can take, and so yeah. So this will be the number of cardinality of the table. So this is what this entire part is trying to say. So so the number of tuples is going to be D1 times size of D1 times size of D2 times size of D3, and this is known as the cardinality of set D1. So the spacing here is a bit too wide. I just realized this. So it's supposed to be the total number of all the total tuples is going to be this. Okay, so far. Okay. So, but however, not all products are meaningful. So, for example, right, if I have a sort of like a family kind of a relationship, right? So I have John and Ellen as the male, Jenny and Alice as the female, and Jenny and Alice as the female, Jeremy and Amy as the child. Doesn't make any sense for me to multiply them together to say that in total it is 2 times 2 times 2, which is 2 2 2, which is 8. So it doesn't make any sense, but because there's it rather should have a subset of the Cartesian product where each tuple is a bit more meaningful. Okay. But having said that, right, why go back to the importance of this Cartesian product, or to know the cardinality of a tuple, right, or rather cardinality of table. It's important. Why? Because it helps us to estimate what is the size of my output, and that will help me to optimize my relational algebra. So I said earlier, right, my SQL gets converted to relational algebra, and in this part it will get optimized. And how it optimized is actually based on these various metrics that are generated to help us see whether what is the right optimization that needs to be done in order to ensure that my SQL query runs as efficiently as possible. Go ahead first. So I can see that this table is equal to this table is equal to this table. The difference between this table and this table is that these are actually switched. But the order of attributes, it does not. It's unimportant. No, doesn't matter. Yeah, so it's not important. So although the attributes are switched, but not important. The difference between this table and this table is also between this and this. So this is in sorted order, and this is in unsorted. So it's also not important. And the ordering of the tuples was not important. So which also means that this is also equals to this. So this one and this table, they're also the same. So the orders of tuples or attributes, they're actually not important. So I now have the first normal form. We'll talk a little bit more about what the first normal form is in the future. But for the time being, take it to be like this is how a relational table is supposed to look like, whereby every single field is an attribute. So there should be no multiple so-called fields in a column. So for example, yeah, so this is not good. Not good. Maybe I'd like to ask why it's not good. Is there a Luo Yuxuan? Or is there a Marcus Ng? Okay, Luo Yuxuan is here. Can you maybe have a suggestion? Why is this not good? Any thoughts that you may have? Maybe it deals with updating of a certain attribute or searching. Should have one value. Yes, attribute should have one value. Correct. Yes, that is what it is required. And the reason why the attribute needs to be one, yeah, yes, Mr. Ui Ming, you want to know consistent separator. Okay, yeah, these are valid points. One of the main reasons why is that you want to be able to carry out search, aggregation, and also update easily. So for example, right, if let's say I have this and I have this, I want to update. I want to find all people without second phone number. There's actually no way for me to do it in this. There's no way for me to do it in this. Yeah. So Mr. Ryan, I'll come back to that question later. So there's no way for me to do it in this context. So the only way I can do it here is I have to take everything and I have to search through all. And as what Mr. Oiming is saying, right, I need to be sure that the separator between the numbers is consistent, so that I will be able to delimitate to tokenize them, and then I will be able to count. So you can tell that a lot of work required on the developer, and in fact makes more work for the developer. So that's not the right thing. That's not the way the DB should be used for. So it should be simple, easier than that. So this is not the right way. Whereas for here, you can simply do one query to select all where the telephone number 2 is equals empty. You can get it done quite easily. Okay, so there's a very good question. Why would they want? There's a question. Why would they want to store phone number in variable character? Okay. In this case, right, I believe that there are things like the extension, there are things like the area code, where they have brackets. So for them, they want to store such things there. Maybe it's a bit more difficult. So I think, and I may be wrong on this. But I don't know whether does variable character able to store non-Arabic numbers or not. Meaning that if I want to write, like for example, phone number like this in Chinese characters, I don't know whether variable character can store this, but it's just a random thought. Yeah, but anyway, yeah. So anyway, this is that. But there's another table another question which I think is very good. Unlimited number of phone numbers. So Mr. Oiming said you can have table with many to many relationships. Yeah, this is actually a very good point. So you can have a table with ID, and then you have ID, phone number, and this will be both will be I'm going ahead of myself, but both will be together will be a key lah. So actually what Mr. Oi is trying to say is that if this happens, right, then I will have a table like this. So I have ID, and then I don't store my telephone number here. I have like that, so ID and telephone number. And so let's say if I have 123 ID 123 and my phone number is 555 and 123 556. So I'm able to store many phone numbers here, regardless of what. So this is definitely one way of doing it. Not without issues, not without issues. The biggest issue I think is maybe updating it. Yeah, but still I think this is typically the accepted way of doing it. Yeah, if it really happens the case whereby you want to be able to store infinite number of phone numbers. Okay, very good. Thank you. Okay, so now talking about keys. Okay, so I'm going to run through these slides, but I probably will go through them again next on Thursday because these are very important concepts. So I divulged a little bit earlier on this, which first when I was answering on the question, talking about key or super key. So these help us to uniquely identify a tuple in a relationship. So so for example, we know that this is unique. So if this is unique, everything with this is going to be unique. Am I right to say that? Yeah. So if SID is unique, so SID as name is also going to be unique. SID GPA is also going to be unique. So because there's only one guy with that particular SID, so everything that has a SID in every so-called every set of keys that has this SID in is going to be unique. So this is what they call a super key, whereby it allows us to uniquely identify any particular row in my entire table. Excuse me. Excuse me. Yeah. Okay. And minimal super keys are called the candidate key. And in this case, candidate key is only SID, because SID is the only unique attribute that's in this entire table. Okay. Any questions on this? Okay. I think this will be a good time to stop. I think the next slide I will have to introduce a lot more other concepts. I will go through this again on Thursday. Regardless, the lectures are recorded, so I'll be posting them also online for your review. I would like to take the next 2-3 minutes to hold in here to answer any questions that you may have. But I'm thankful that you have chosen to spend this evening with us. To remember to log in your attendance. Thank you so much for your time and attention. I'm happy to take any questions